Good morning to everybody. Today, let's start the lab number 5. In this lab, we have a different number to do, particularly important. And as always, when I'm describing these things here, I will refer to the theoretical part. All right. So we have launched the software. And for today, as I told you, we will face two different aspects that are very important. The first part concerns the radiometric calibration, and therefore the whole part that we have described in the theoretical part, and we have described it in a chapter that concerns the basic radiometric pre-processing. And these are the processing that should be done in order to work with physical value of reflectivity. And in the second part, that is particularly important, that is following the part of the radiometric pre-processing, that is fundamentally about the possibility of extracting and working with what is called the region of interest. We will see the acronym ROI. Okay, let's begin to make the presentation. And so we are still using our data, and let's open this data as open as optical sensor as usual, Landsat, GeoTIFF with metadata as usual. You see here. All right, let's go in the northwestern Italy again, you see here, and let's open Landsat 8. So you see we have double clicking here on the metadata text file, and you see we are opening the color image as in the preferences, in the general preferences at that particular scale. And what we can see in the data manager, you see here from the icons, we can see that we have available, let's enlarge the windows, all right. So you see here, we have the three different data sets, all right. In this is Landsat 8, I remind to you. So, for example, here, we have here the reflectance data set, and you see this is acquired in the 14th of April 2020, so during the lockdown of the last year. So we have the multispectral part here, you see, with 4 different color band, I mean a visible band, and we have near infrared and middle infrared. Then we have also the panchromatic here, that is a higher geometric resolution. Of course, only one single bands. Then you see we have also this band that is called Cyrus, that is, and then at the end we have the thermal infrared bands, the 2 thermal infrared bands. And then we have also the last one that is the quality image, that is referring to the quality of the whole data set. All right, so let's see how the data are displayed. So, I mean, you remember that here, just exploding this button, we can see in the layer manager, which is the color composite. So you see that we associate to the red, green, and blue the 3 bands, and you see here we have the name of the file, and right clicking, you see with quick starts we can generate the statistical distribution of the data. So these quick starts, I remind to you, are processing that are made out of the data, and are particularly important because they give us a very precise notion of the quantitative aspect of our data. Therefore, beyond what we can see at the moment, we have images that, I mean, apart from what we can see with our eyes, we are entering in the distribution of the data from the statistical point of view. So you see here, we have this window in which we see extracts in the tabular part here, in the lower part, all the values, the statistical values extracted for every single band. So you see the minimum value, the maximum value, the mean value, and the standard deviation for every single bands, for the 7 different bands. So you see here that the mean value here in the blue band is represented here, you see in this diagram, where in the x-axis we have the wavelengths, you see here, and the y-axis we have the digital numbers. And you see that all these values are very low in consideration with the possible maximum value. And you see that, I mean, this radiometric resolution is larger than 8 bits of the Landsat 7, but is more than 8 bits. So we have a higher geometric resolution. So I remind you that we saw also that in this plot window, we can also see, you see the different histogram. This is the histogram of band 1, the blue band of the first data set. And you see that this histogram, this sort of bell of the distribution is very close to the origin. So that means that in terms of luminosity, this image is quite dark because all the values are compressed there. And you see, we can also add all the other histograms of the different bands you see here. All right, so we have a look to the characteristics of the data. So let's close this window. And let's start with a new series of processing that, and we will start saving files. And starting to save file, we will get used to save this file. And in order to save this file, you remember that we will change the original distribution. So let's talk about the radiometric pre-processing in this moment. And basically, they tend to convert values, changing digital number of the original data into a series of new values that, I mean, are strictly in reference, with reference of the way in which the surfaces that are represented by the cells are reflecting or emitting energy. So we want to pass from this digital number to real values of radiance. You remember that when the radiance arrives to the sensor, whether it's generated by reflectivity or by emissivity, this radiance is striking over the detector of the sensor. And being this sensor digital, this quantity should be sampled in a digital number. So there's the possibility of sampling this data with a digital value, and this sampling function, that is a way in which the radiance value should be converted in digital number. These function, these resampling function, are known because, I mean, they are a characteristic of the sensor itself. So, I mean, these functions are known for the majority of sensor in order to proceed with this kind of conversion. So, working with digital number is something that I mean, is annoying for us, especially because we have a very strong limitation. We want to come back to the physical values, so to values of radiance. And in order to come back to radiance value, we must basically remember that we need to perform the inverse passage to the analog digital conversion. So taking the digital number and convert in a backwards processing, take these digital numbers, pass to the same function that converted them into from radiance to digital number, come back to this same function and passing back and reconverting that from digital number to radiance value back. So we are using the same function as I explained during the theoretical part. So you see, if I'm right-clicking here, we saw that that these conversion data are on the metadata part of the file. You remember? So, for example, if you are going here, view metadata, you remember here. So, for example, here we have the map info, we have also the coordinate system, the extents of the image, and the spectral values. Let's enlarge these windows, as you see here. And when we are having a look, I'm just opening these things here. When we are having a look to this table for the spectral part, you see that here we have the 7 different bands with the band's name in the first column. You see with the conventional name that has been assigned to these particular bands. Here we have the central wavelengths. This is the precision, and this is the gain and the offset. You see, both in terms of radiance and in terms of reflectance. So we have gain and offset in terms of radiance and reflectance. So these numbers are nothing more than what we have introduced in the theoretical part. That is the way in which they are, for example, the gain is the slope of the linear function or the conversion that allows to convert radiance to digital number, and the offset is the point in which this linear function is intercepting the y-axis, as you remember from the theoretical part. So, which is the difference between radiance and reflectance? Okay, you know that the radiance was introduced in the second lectures in which we talked about the radiometric systems, and so the radiance is what is coming from the Earth's surface to the surface of our detectors, while the reflectance is something that is very simple. Reflectance is nothing else than a normalized radiance. That is, therefore, is a radiance that is represented in an interval comprised between 0 and 1. So if I have a set of radiance measured for every single cell of the matrix, I will check which is the maximum radiance of the distribution, and I'm dividing all the other radiance by the maximum one. So, of course, all the values will be comprised from 0 to 1. This radiance, normalized radiance, is what is called reflectance. Why it is necessary to have a distinction between these different things? Because if I want to, for example, if I want to perform a multi-temporal analysis, so for example, I want to check in the course of different weeks in different time intervals, as particular surfaces are changed during that period, in order to perform this comparison from the analytical point of view, and therefore from the data point of view, I cannot work with simple radiance, because the radiance are obviously, as was mentioned in the second lectures, are functions in comparison with the same surface. The quantity of energy reflected in this case that is depending from the flux of energy that is coming from the sun. And so you know that having the same reflection coefficient rho for the same surface, the quantity of energy that is coming from the sun that is striking over this surface is function of the angle of incidence. So I mean, this angle of incidence of the energy that is coming from the sun is changing in the different time interval. Because I mean, it depending from the geodetic characteristics of the Earth rotation, and for example, is depending from the hour in which the acquisition is done, and also is depending from the seasonal variation. Of course, it's depending definitely over the latitude of the scenes. But of course, this incidence angle of the energy that is coming from the sun that is striking over the surfaces is depending on the period in which I'm acquiring this data. So during different weeks, of course, this angle is changing, and so the quantity of energy that is striking over the surface is changing. And so in order to compare this radiance value over time, we need to have a normalized value. So having this normalized value, we are taking rid of this incident angle, and we are having values back after the calibration that is allow us to compare different measurements performed in different time span. So let's get used that our calibration usually must be done in reflectance. So we can close these windows. And another extremely important aspect of our this lab is working with this calibration. So let's go to the geometric correction, geometric pre-processing. It's not there, but you see for the first time we are going to the toolbar in the right part of our graphical layout. So I remind you that now whatever we done till now, it never led to saving files, while instead a mass part of the operation we will do from now on will comprehend the facts of saving files. And this is quite important. So you see here in this folder, you see we have this folder that is Radiometric Correction, all right? So you see here. So we are pre-processing from the radiometric point of view the original data. So let's explore this radiometric correction. You see that we have a series of operations that try to basically calibrate both from the point of view of reflectivity and also from other operation. They are trying to perform this operation. So you see, in this case, you see we need this radiometric calibration menu, you see here, that is directly go to read the metadata, in particular the ETM sensor mounted on board of Landsat, and this calibration that now we are we are going to perform will be used also with the Landsat 7, of course, if you have the metadata file, because otherwise, I mean, it's really difficult to do that. So pay attention to this calibration, and we are doing that in Landsat, and you will see when we will use Sentinel, we will need something different, so other sensor. So okay, in this way, we are performing a calibration that is called usually top of atmosphere calibration. So top of atmosphere means that, we have the radiance or the reflectance as measured in the external surface of the troposphere. So, I mean, in this case, we are not taking into account the correction due to the scattering, to the selective scattering and to the non-selective scattering. So, I mean, top of the atmosphere, that means that we have already calibrated data because the data provider has already corrected these things here. But in general, there are no correction regarding to the what is called the bottom of the atmosphere, that is encompassing also the correction due to the atmospheric scattering. So in order to launch this operation, we double click in these things here. You see we have the file selection windows. This is a very important windows because it's very common to all the other operation we will face from now on, because in these windows, you have the possibility to select all the data that are already opened in the data manager. So I mean, whatever processing we will perform, we will see here what we have opened and is present in the data manager. You see, here we have the different 5 different data sets, and for example, you see here, I have also spatial subset and spectral subset. You see, for example, in the first data set, full extent, that means all the bands. And for example, if I'm going here in the other bands, you see that we have a different number of the spectral subset. So if I'm exploiting these file information windows, you see, we can get all the information concerning this particular data set that are embedded in the same file. So you see, we have here all the principal metadata in order to better understand the data. So the first of the list, you see, is what we want to work on. So the 7 different spectral bands of the Landsat 8 sensor, multispectral sensor, that is available. So having said these things, what we want to do in these windows that is common for, common for every single, processing in order to select the data. Apart from the selection of the data, you see, we will have always the possibility to define the spatial subset and the spectral subset. What does it mean, spatial subset? You see here, full extent. That in this case, we are processing the whole image. That is the full extent of the image. So, if we are clicking here, you see, there's a right part of the windows in which you see here, we can define a subset of the image, not processing the whole image, and you see we have the red frames around everything. So this is particularly important because, for example, we want to exclude the background of the image, so the black part here, because you remember, it's not part of the image, but it's part of the background that is used in order to inscribe our image. So I can decide not to process all the whole image, and in order to define this subset, you see here, I can define the upper left point in terms of columns and rows, and I can define also the right lower point in order, again, in column and rows in the image matrix, in order to define this subset. You see here, in order using this numbering is not very simple because it's not easy to understand. Well, you see, I can do that interactively because I have this red frame, and so if I'm clicking this red frame, you see, I can drag and define a subset here in order to perform these things. You see here, I can use again the full extent. I can use the view extent, so what is shown in the main windows here. You see here, I can subset I can subset for another file. This is not the case in these things. I can subset, you see, by vector. For example, if I have already a vector defined, for example, a rectangle in geographic coordinates, and I also subset by ROI, by region of interest, but I will explain region of interest. Or I can enter map coordinates. All right, in this case, let's use the full extent, because we can use full extent in this case, because if you see, if I'm using what I'm seeing here in the layout, is you see here we have the position in the matrix, and you see that is the dimension of these things. I can move these windows, you see here. Okay, let's come back to the full extent. We are processing the whole image, all right? So, spectral subset. What does it mean, spectral subset? You see 7 out of 7 bands. You see, it's very simple. We can perform this processing not working with all the bands, all the spectral bands, but I can use only a limited number of bands. So I mean, so I can define a smaller subset of spectral bands. So you see, I can only select these blue and green, green and red, or I can use also the keep in press control, the mid-infrared, for example. You see. And I mean, I can select a different number of bands. In this case, we are not selecting a spectral subset, so we are selecting everything because we are processing all the image, the whole image, and the whole spectral bands. So you see, we didn't change anything, but this is the very first time that we are having a look to these particular windows that will be very common for all the other processing phase. All right, so in this time we can, as you see, we haven't changed anything, so we can press OK. So you see now we have these windows. This is the name of the windows, Radiometric Calibration, you see here. And you know that every single windows of ENVI have a particular name. Here we have the different fields. This is calibration type, radiance or reflectance. So let's get used to use the reflectance value, because now we are calibrating a data sets, but you know that we have also other data, for example, the one that are coming from the Landsat 7. So I mean, if we are using the reflectance calibration, in this case, we will compare that, for example, with other, in a multi-temporal approach, with other data. Otherwise, if we are using radiance, we cannot do. So let's use reflectance. Interleaved of the output. You remember that this is the way in which the multispectral data are recorded in a single file. Let's use the BSQ, the band sequential. Don't modify anything. All right, because I mean, it's better to use the same. All right, then output data you see here is float, so we can change the declaration of the variable. In this case, we are using different bits. In this case, when we will convert this data, the results that will be a real number comprises between 0 and 1 with a certain number of decimal digits. I mean, we need more bits in order to store the results. So, I mean, in order to do that, we are using the floating points. That is a number that is namely is stored in 3 different bytes. That means in 24 bits in order to store all the possible accuracy that we have for real value. So that is due in order to memorize this particular value that are coming out from this conversion procedure. So we need a more number of bits in order to store these results. So let's use in this case the floating point that if I'm not wrong is I don't remember if it's 2 or 3 bytes. This is the scale factor. I mean, in this case, all this value will be included between 0 and 1. That means that all this value will be in this range. But I also change the scale factor, but I mean, this is not really important. We are not modifying also the other values. And so now you see, we are putting the name, so we are selecting the position. So for example, I'm changing my download and another one here. You can, of course, choose whatever you want. Then here in the name of the file, I can use the real name. So let's establish some rules for these names. So you remember that from this here is what I'm suggesting to you. I'm just taking the original position of the file. All right, I'm going here, Landsat 8. Okay, so what we can do is just to use the original name. You see, that is, I'm suggesting these things here, one of the different bands, in order to have all the different name. You see, I can erase the last part, in order to keep all this information that are important, because you remember, here we have embedded the dates, the type of sensor, and so on. And then at the end of the name, if I'm using these things here, I not lose any information that is coming from this original name, that is the download name. So for example, I can just put down underscore cal, that stands for calibration, but adding this suffix calibration cal underscore cal to this original name, it reminds me all the information that I have from the original file. So I'm keeping these things here. I'm copying this name. I'm going again to the download here in another things, and so I can change with the original name and at the end the underscore cal in order to have a reference to the fact that is calibrated. All right, and at the end I can also add a more other information, that is, for example, the way in which I can open that. So that means that the name is okay. So this is the first time. You see, there's also a check here, display the results. So that means that once finished the processing, the results will be displayed in the view. So clicking OK is starting. So you see here in the right lower right part of the part, radiometric calibration, you see that is processing. I remind you that these files are quite big. It's more or less 8,000 by more than 7,000. So that means there are around 60 millions of cells in 7 different bands. So that means that there are more than 400 millions of values. And you see that is already finished. You see? And my PC, my laptop is not particularly powerful, but you see that the processing is done. And you see that is still proceeding, and is proceeding with the raster pyramids that I introduced last time. That is the way in which you can speed up the display of the image. So you see, and we are here in the top of the list here in the layer manager in the same view. And you see that enlarging that, we have the new name of the file, what we have assigned. If I'm exploding that, you remember that we have that in the preferences. This is a true color synthesis. So if I'm going to the data manager, you see in the data manager, we have at the end of the list, you see here, we have the new calibrated file. You see here, that is inherited the original name of the bands, you see, here. All right, so let's close it. Now we perform this calibration. In order to understand what is happened in this calibration, right-clicking with the calibrated file here, you see, and we can perform the quick starts again. So now we are extracting the statistical characteristics of the data. Let's check what are these characteristics. Okay. So it's generating this data. You see, here is processing all the data. You know, the first time is quite slow, but I mean, will improve next time. Okay, I'm just going to the original file. So I'm going to the download. So here is the original folder where I take the original data. So Landsat 8, you see, just to have an idea, these are my original files. For example, if I'm taking a bands 1, you see the 7 bands are more or less something like 120 megabytes of data, the original data. You see that originally was 8,000 by 7,000, so that means 60 millions. The data were stored in 2 different bytes. You see, 60 millions for 2 bytes is 120 megabytes, around 120 megabytes. If I'm going to the download folder in order to check what is happened to our data, you see that the data that I store, that I have processed in the 7 different bands is 1.7 gigabytes. That means that divided by 7 bands, you see that the data is is around 250 megabytes of data for every single bands. So that means that in order to store this real data of reflectance, we need more bits. In this case, they used 4 different bytes to store these results. So you see that in that few seconds, we produce around 2 gigabytes of data. So pay attention from now on that every time we will process this data, we are creating a bunch of new data, and so pay attention to your hard disk. So you see, here now we have the statistics, all right? And so you see, all these data are stored between 0 and 1. You see that we have data that are over 1.5, but this is a sort of bias that we have on the data. But you see that, I mean, apart from the maximum, for example, if I'm going to the histogram of band 4, no, let's say, well, band 5, for example, the near infrared, you see this is the histogram of the band 5, that is the near infrared. These all values, this maximum is the background, you see. But you see that we have also that in band 4, that is the background. This is not part of the image, you remember that. So I mean, it's not part of the image. So it's the background value that is equal to 0 in that case. All right, and I mean, in this case, you see the calibration is changing the distribution of the data. So performing this calibration, we need to see the data that is converting top of the atmosphere value. We need fundamentally to convert this reflectance in order to model the atmospheric scattering. You remember that in theoretical part, there is the possibility of doing this using a particular operation, a particular algorithm that is start from a very trivial assumption that, as we know, the atmospheric diffusion, especially the selective one, is a diffusion, is a scattering that basically take place in the visible, and in particular is affecting the blue part of the visible, that is the color of the sky. In particular, in every single image that we are acquiring, we are almost sure that on the image there will be some shadows, right? Because also if we have a very flat surface like the sea, due to the effects of the waves, for example, and the inclination of the sun, we will have some waves also on very flat surfaces. So if we have these shadows in the visible, that should happen that these shadows should not reflect any contribution in the visible. So if we have this contribution over the image, that means that it's coming not from the surface, but from the troposphere. So that means that if the minimum of the distribution is not equal to 0 in every single band, the minimum value is related to the fact that we have scattering from the atmosphere. So this is nothing more than the bottom of the atmosphere calibration is coming from the selective scattering. You remember that in the theoretical part, we call this algorithm as dark subtraction. So the subtraction of the darks that are the shadows, and you will see here that in this list, in the toolbox, we have this dark subtraction. You see here? So double clicking here, you see I have this information. So you see how we can select these different input files. So if I want to perform this dark subtraction, I'm using the already calibrated file, of course. So you see, in these windows that is typical, we have all what is available in the data manager. So I'm quite sure that the last one, you see here in the file information, you see this is the file that is _cal, that is the description calibrated of top atmosphere reflectivity from this file here. You see? So in the file information, you can get all the information. Of course, you can enlarge also the windows in order to have all this information. So when we have performed this information, ENVI in the description is remembering what kind of processing we use, and so is reporting this information also here. All right. So in this case, I mean, we have also this that is coming from ENVI. So let's select these things here, but pay attention. The spectral subset, we are using all the bands, but in spatial subset, you see here, we have something that is different from before. You see, we don't have anymore the metadata file in this case, because the metadata file was for the original data and is not available anymore for the other file. So you see, we have another different windows, but we have the same information. You see, you can define the spectral subset by defining upper left and lower right coordinates. So if we want to select all the different image, map, file, and ROI AVF, if I'm clicking here on this button image, I have what was shown before. So let's select a subsample. And why we are selecting a subsample? Because we don't want to have these edges, because I remind you that these edges, this background, is equal to 0. So if I'm taking only one single cell of the background, the results will be the same of the original, because if we have a value that is equal to 0, I mean, nothing will be done in the dark subtraction. So, and we are also selecting a subset in order to speed up the operation. So, for example, I'm selecting these things here, just to have something that could be similar to everybody. Let's select a subsample, and you see here, I'm selecting 2,500 for both samples and lines, and you see I'm forcing that by entering the data, and you see I'm putting that encompassing Torino. You see here I have Torino, but pay attention to stay away from the borders, from the background, in order to not encompass also 0 value. So let's press OK. You see now we have these values, 2500s by 2500s. Let's OK. Okay, the spatial subset you see here is defined. So we can click OK. And you see this is the dark subtraction parameters. So we have different things here. So you can select in the subtraction method. We have 3 different options, and you will understand immediately what does it mean. So how I can perform this calibration. Or I can look for the minimum of the band or the single bands, or I can use the region of interest, or I'm having a user value because I measured that on the ground. I mean, you see, the region of interest is not active because, I mean, we don't have available a region of interest, but I mean, it's particularly complicated to find the region in shadow here because it's not very easy. So, I mean, let's use the band minimum. We can save this file, you see here. There's also the option compress. Don't never use this compress option, because this is a compression operation that could be destructive. Let's choose the name of the file. You see, I'm going again in download. I'm taking the last name. You see that the original file, this was assigned an extension .dat, you see, and there's also the same file with the HDR file, that is the header. Let's remember these conditions, because I will explain that after a while. This is the header that was created by Envy, and we will see that later on. So I'm taking the original name of the data, the underscore cal. I use the same name, and I'm adding another things here, another underscore, and I put that DS, that stands for DAS subtraction .dat. This is the original matrix. And I click on open, and I perform the operation. And you see, the operation is still and already done, and it has already built the pyramids. I'm taking out the visibility of the others. You see, it's here, all right? You see, there's nothing, but I'm out of the, because you remember, I use only another things. This is the data, you see? I'm closing the overview. This is Torino, you see? And I'm bound that, and this is calibrated bottom of the atmosphere. As usual, right-clicking on this file here, top of the list of the layer manager in the view number 1, I'm performing the quick stats. That is really quick because, I mean, the image is only 2500 by 25, and these are the values. You see, the 7 different bands. The minimum values that you see is very similar to 0. The maximum value should be 1, but due to the approximation is more than 1, but don't. This is also the part of the window where we have every single values, and you see it seems to work. If I'm going, for example, to band 5, you see here, this is we don't have anymore the maximum close to the 0 value, because we have avoid the background, and you see that this is a histogram that is very similar to a Gaussian, to a normal distribution. So, for example, you see here, if I'm going the band 4, you see that it's quite different. Band 3 is different from band 5, for example, from the near infrared. You see, there are different shape of the histogram function. So pay attention to the scale of the scale, because it's from 0 to 60,000. That is not really the right scale, because, I mean, this is the counting. This is the counting of the cells that have that particular number. All right. While on the x-axis we have the value that are, I mean, the wavelengths that are related to the different spectral bands. All right. So you see here we have the wavelengths. All right. So very good. So I'm closing these windows. So now we have this data. All right, and this data is processed and now is ready to be used. So we, from the toolbox, you remember, we perform the radiometric calibration, and then we perform the DAS subtraction over the already calibrated file. So if we are going to the data manager, you see I'm enlarging the windows. You see that bottom of the list I have also the DAS subtracted information, and if I get the file information, you see here I had in the description, this is the results of the file. Well, you see here, in the before we have calibrated top of the atmosphere. Well, you see we have another information in the dark subtracted one. You see dark subtraction results. You see, so this is the surface reflectance. That is what is called bottom of the atmosphere reflectance. All right. So let's close this window. All right, and let's start with another part that is related to the extraction of the region of interest. In order to start with the region of interest, we have always a couple of possibilities. The first one, just using this calibrated file, we can right-click from here, and you see I can open this function, new region of interest. All right? The second option is just going to the icons bar, and you see here we have region of interest, right, too, that are pointing to the same, of course, procedure. So you see, if I have these icons that I can do and perform the same operation. Let's click the icon. You see, this is the windows, and this is the region of interest tool. This is the name of the windows. But before doing these things, before starting, let's do another things. So this is the region of interest opened. You see, I can just give up the visibility from here, and I'm using the original file, bottom of the list. You remember the original file that is not converted into reflectance value and not thus subtracted. All right, the original data. Okay, in this case, you see, I have a visible that is open. I want to change the color composite. So, for example, I want to use the region of interest tool from this particular data set, from the original one, not the calibrated one. So I'm selecting these things here. I'm right-clicking here, and I'm changing here the RGB bands, for example. So I'm changing the bands. So you see, I can use a false color, where to the red I'm adding the near infrared, to the green channel the red, and to the blue channel the green bands. Once selected, we can click OK. You see, this is typically a false color. All right? So we can do also this operation from the data manager, you remember. And we have another way to perform this analysis. Here, you see here in Torino how we can understand that we are in Torino, because if we are going here in view and we are going to the reference map links, you see here, we have these windows, and you see, I mean, there's script error, but it's a bug of this version of the software. But you see here that we are in Torino. I'm going to zoom in, you see here. I'm using the pan, and you see when I'm zooming on these windows, also in the reference map, I'm zooming. So, for example, if I'm switching here from the base map, if I'm going to imagery with labels, for example, you see here, closing it. All right, for example, here you remember that these are the FCA facilities. You see that if I'm using this image, there are very high resolution images, also aerial images, and you see if I'm zooming in, of course, I mean, I have a very high resolution image. Of course, I mean, to perform this operation, you should be connected to the network, to the internet, because this service is coming from a server in the States. You see, for example, here in this case, we have a natural park of Stupinigi, and you see here, in this central part, you see here, I'm zooming and zooming in a little bit. You see here, this is nothing else. That is a castle that we are south of Torino that is called the Stupinigi Castle, where we have a very large park that is surrounding the castle. You see here, for who is foreigner, it's a very nice place to visit, for example. I see it's too much zoomed. You see, it's not enough. We don't have any images here available. So you see, let's check if I can zoom in. You see that there's a part of the castle. All right, I'm zooming in right now. I have some issue with the network. So you see that what we have represented here is the part of the castle where you see, I'm sorry, it's not working. All right, you see I have some issue with the internet connection. You see that this is the castle. I mean, it's not really easy, very bad, but this is the castle, all right, in very high resolution, all right. Unfortunately, I cannot use that in this particular moment. Some network connection issue. So why I want to use that? Because I mean, you see here the vegetation. We are sure that it's vegetation because it's very reddish, and these things coming from the near infrared. So let's go to the menu region of interest. What is a region of interest? The region of interest, we describe that also from the theoretical point of view. So we are applying a statistical function that is nothing more than the extraction of a sample of radiometric values from the whole population of the radiometric values of the whole images. So that means that if we have here an image that is 8,000 by 7,000, we have 60 million values of digital values that are more or less similar to the Italian population. So we have 60 million cells in this image, and we have 7 different spectral bands. And out of this population of 60 million values, we are extracting a sample of these values that is allow us to verify the characteristics of the sample itself. So, for example, if we are extracting these values from out of these 60 millions, we can have this very small sample of the digital numbers, and all these samples should be representative and also significant. So that means that during the lectures, the representativeness and the significance of the of the samples is how many values we have in the sample. And for example, if we are taking about a political election, of course, where we are performing this kind of operation, for example, in order to have a representative sample, we need a certain number of individuals, while the significance means that, I mean, we have a limited variance of the values. So that means they should be homogeneous in order to have a very low standard deviation from the samples. So I mean, the region of interest is strictly correlated with the statistical procedure that is related to the sample extraction and processing. So for the region of interest, so means that we want to extract some characteristics of homogeneous surfaces. So, for example, if I'm extracting a region of interest of vegetation, for example, I can understand the characteristics of the vegetation itself. So, in this case, let's look at this menu. So you see we have the different menus. We have this file menu, for example, where we have open import vector. For example, open, we have already defined some region of interest, and we can, for example, reopen that. We can import vector because, for example, we have in ArcGIS these things. You see, these options are not available right now because we don't have any region of interest already active, and we have here the online help. So you see here, in this case, we have these icons. Most part are not available. From here, from the region of interest manager, we are in the phase of defining the first geometry, the first region of interest. And you see here we have geometry, pixel, grow, threshold. In this case, let's forget pixel, grow, and thresholds because they are something that we will use for other operation. While here, this tab, very important, is geometry. Why geometry is so important? Because we are going to extract this region of interest in a graphical way. So extracting this sample from the population of the whole digital number, we need to understand how to extract these values. And so in order to extract this value, we can draw polygons, for example, here in very homogeneous areas, extracting all the values here. We can use, for example, here a rectangle. We can use an ellipse. We can use a polyline that is will be extracted all the cells that will intersect this particular polygon, or we can select points. In this option, points, we are not talking about points, because if we are talking about the statistical way to extract values, if we are extracting only one single point, the representativeness characteristics of the samples is not anymore valid, because if we are extracting only one single cell, the samples that we are extracted is not representative of the whole population of 60 million values. So we are not using the single cell extraction. While we will use polyline, of course, for linear features, and we will see that later on, and we will use especially polygons, and sometimes also rectangle. But I mean, in this case, very regular figures like rectangle is not something that I suggest to be used because I mean could cause some problems. So let's use different samples, different geometrical samples, but actually the most used will be to draw polygons with our hands, with the mouse. All right, so in this case, let's use the polygon. So let's use the polygon. And what is means extracting a region of interest? It means to draw these polygons. So let's zoom with the wheels of the mouse because I want to digitize here. And so I have this span, so now I have the selecting option, and in selecting options, I will draw a polygon, but not using these options here. I'm sorry, I need to go here, so you see I have some problem now, because it's flickering. I'm sorry, I'm closing that, and then reopen that with the option. All right, I'm going to the geometry again. Okay, polygon, and now you see now the mouse is it's changed in something different. So by right clicking, you see here I can just keep impressed the values. You see when I'm going to close the polygon, I can release the left button, and I'm clicking the right button of the mouse. And you see I have this pop-up menu, complete and close the polygon. So I can change the colors in this case because it's using the red. You see here, I can, for example, select the green, you see? And this color is very important, and you will understand the importance of the color when we will talk about classification. So you see, let's change also the name. Also the name is very important. Let's call that vegetation, for example. You see here, I take out from the image, in the sample, a series of cells. You see, I draw on the image, stay away from the border of the image. You see, here there are some borders that are darker. What are these borders? these borders are essentially path or roads that, of course, this is not vegetation. So I mean, when I'm drawing a region of interest, I need to take something that is very homogeneous from the radiometric point of view, so that I should stay away from the border. All right, so if that borders are not red, of course, they are not vegetation. So, and then, staying away from the borders, I close these polygons and extracted this cell. So in this case, you see, in the file, you see here, in the principal menu, I can save this region of interest. I'm not saving that because, I mean, it's a very simple things here. Okay, so consider that in this case, these region of interest are available and they are in the memory since this MV session is active. So if I don't say, I'm not saving that right now, I mean, if I'm not closing MV, that will be available. And you see, when I draw this polygon, I use cartographic coordinates drawing that, not directly, but you know that the image is georeferenced. So I mean, I can use these polygons and I can use these polygons in other software that are using cartographic coordinates. What I can do right now, for example, I can go zooming out and pay attention that still I have this kind of cursor. You see here is active the possibility to draw. So pay attention, select here, for example, the selection tool, in order not to have active that. You see that we have not active the region of interest tool. So for example, you see that we have the river, the Po River here. You see here that is very dark in the first color, because in the near infrared is not reflecting anything. So you see that in the northern part of Torino, you see that there's a confluence of two different rivers. Or I can go, for example, you remember here we have two very small lakes that for who is living in Torino, they are very, very popular, that are the Avigliana lakes. So in this case, here you see also south of Torino, we have in the Po River, just close to the close, these are lakes, these are the artificial lakes, and they are very dark because, of course, in the near infrared they are not reflecting. And these are artificial lakes that are quarries where they are extracting sands for building usage. So, for example, if I'm going there, I'm going to the region of interest again. You see that now the mouse is changed. Now we are in the vegetation. We can have another things here. For example, you see that now they are active, these new icons. I can click on this one, new ROI. You see, I can define a new color, for example, the blue, that is because I'm going to water. And here, for example, I can call that, this is in Italian, but I can call that water, all right? So I'm drawing here a polygon staying away from the border, so in the darker area, and when I want to close this polygon, I release the left button of the mouse, I'm clicking with the right button of the mouse, and I'm closing with the pop-up menu this polygon. So you see that now I have another polygon. So using these particular icons here, you see I can remove, I can select the next ROI, and I can do other things. So if I'm moving here, you see, I can move from one region of interest to another. And for example, you see, now I can go to the facts that now I can save. I have a couple of ROIs, so I can save these ROIs. So you see, I have here. Now the water is selected. I'm selecting both the ROIs, and you see that we have also the ROIs here in the layer manager, and this is very important to have that. I'm saving that. I'm selecting the name of the file. For example, here, I can call that ROIs in general term, but pay attention, okay? It's the software is assigning XML extension, and I'm clicking OK. So I saved this ROI. So now I'm in the safe position, because if I disconnect from MB, I will have that field. And you see that if I'm going to the layer manager, you see right-clicking, I can go to the different ROIs. You see when I'm clicking, for example, in the water, and if I'm right-clicking and I'm going to go to item, you see here, I moved to the item. So, but you see that the region of interest are still in the layer manager, all right? Because they are polygons, they are graphic entities. What I can do with these things here, you see here, I can go to the vegetation, right-clicking, go to item, here it is, and you see that is vegetation also in these windows here, all right? So I can pass from one ROI to another, but I can do another very important things. When I'm clicking on this region of interest, in the options, you see here, these are all the possibilities that I have right now that I have different region of interest. I have this possibility to compute statistics from region of interest. This option is still in these icons. You see, compute statistics. This is a very important option, and you see, compute statistics. You see, I'm doing the same quick stats option of the image, but done only in the region of interest. This is a very, very important operation I can do in Envy. So you see, as usual, starting from the lower part, you see I have the tabular statistics as before. We have the 7 different bands because these ROIs was extracted for all the bands. You see I have the minimum, the maximum, the mean value calculated, and of course also the standard deviation. And you see here, in this region of interest, I extracted 34 cells. That is quite small. And you see that is also the covariance and the different other values, the eigenvalues and other things. And here I have also the histograms for every single region of interest, all right? So that means that these are all the values that are encompassed in these values. Of course, in this case, we have these particular values in which I have the number of cells that are represented in that particular value. What is very important here is the diagram here. This diagram is representing a very important piece where in the x-axis we have wavelengths as usual. In the y-axis we have the data value. So I mean the value that is coming from the digital number. This function is very, very important, and we have described that in the lecture number 5 in the second part, that is referred to the interaction between the energy, the electromagnetic energy that is coming from the sun and the surface on the ground, because this is what is referred as spectral signature. So this is not a single spectral signature because we have a sample that is done by 34 different values. And these different colors, you see, the black line, as usual, is the mean value. The 2 green lines of this belt is the standard deviation plus and minus in comparison with the mean value, and the red lines are the the minimum and the maximum value. So let's have a look to the statistical characteristics of that. So we have extracted only 3-4 cells. So from of course from the statistical point of view, 34 cells are very low in order to understand the values, the 60 million values, and I mean, we are taking into consideration also a very small area of the whole images, and you saw that you know that the whole image is more than 200 kilometers by 200 kilometers. Here in 30 cell at 30 meters on the ground, we have 1 square kilometer, not more. But is this sample significant and representative? Significant means very low standard deviation. And from the graphical point of view, you see that the green values, the green lines, are very close to the black lines. So that means, and you can understand that from the graphical diagram, the standard deviation is very low. And you see that in these particular bands, you see, is the standard deviation is larger. So that means that in band 5 here, that is the near infrared, you know that the different kind of different types of vegetation are reflecting in a different way. So that is the reason in which we have these things here. So in this case, you see that the spectral signature is very similar to the vegetation. We have an absorption peak here in the red. We have an absorption, a reflection peak in the near infrared. But you see here that in the blue bands, in the first two bands, we have a very high reflection. So considering the theoretical spectral signature of vegetation, you see that it's quite similar, apart from the smaller wavelengths of the visible, that means in the blue band. But I want to remind you that the data from which we have extracted this region of interest is the original data. So it's not bottom of the atmosphere calibration. So that means that we have also scattering coming from here. You see from here, we can also see the different histograms. For example, if I'm taking the histograms of band 5, you see that is the histogram of the ROIs. You see that is making not really sense in this case. While if you are taking into consideration this spectral signature, taking into consideration minimum, maximum value, mean, and standard deviation is very important. This is the spectral signature of vegetation. So if I'm closing to icons that things here, if I'm going to the water here, you see here, and I'm clicking to go to item here, for this water spectral signature, I can extract with the icons the statistics. Again, you see, as before. So you see, this is the spectral signature of water. You see, that is very significant because we have a very low standard deviation. You see, the green lines are very close to the black lines. The reflectivity peaks that is quite low is in the blue. As it decreasing, you see here in the red, and then it's very close to zero when we are passing through the infrared spectral bands. You know that the infrared spectral bands are very absorptive. They are absorbing all the energy that is coming from the sun when we are facing water. So I'm sorry, I need to put that. So I'm going again to the vegetation. I'm going to items. I'm extracting again here the spectral signature. You see, we have side by side the two different spectral signature, left water, right vegetation. So now we have performed a fundamental operation that is, the extraction of spectral signature. So these are the two spectral signature. Don't worry, because we will extract many other spectral signature. So let's close these different windows. So you will fully understand how to extract spectral signature, because we will do that several times in the future. So let's going to close these windows here. All right, the spectral signature. So from this point of view, you see, in order to have more representative spectral signature, we need to have some other polygons, for example, of vegetation or water. But a thing that we can do is that this layer of vegetation that you see I have selected, if I'm clicking, if I'm dragging these things here, I can put that in other position. So, for example, I'm moving that to this image. That is, I'm sorry, I want to move that in another image. I performed the wrong operation. So this is the calibrated. I'm taking these things here and I put in here. All right. So you see, this is the calibrated and thus subtracted image. You see? In this file, that is the calibrated and this is the first, the multispectral. Then I have the CalDS. Okay, I have in the CalDS the vegetation. Taking out the visibility of this one. So you see here, I put on the visibility, switch on the visibility on the first one. All right, in the calibrated and thus subtracted data set, and you see that the ROI is there because I moved that also under these in the views in the layer manager, just in the data set. Let's go to the data manager because now we have the visible. You see, let's go to the data manager. I'm sorry. Okay, we are changing that to the false color. So we are going. Let's open that because otherwise I get lost. Okay, this is the dark subtracted. I'm going to the band selection. I'm adding to the red channel the near infrared. Okay, this one. All right, and I'm associating that to the red band, the red to the green band, and the green band to the blue channel. And I'm loading the data. All right, I'm closing the data manager. All right, so we are here, okay? And now you see I have, say if I'm selecting vegetation, you see, okay, from the original, if I'm clicking on the right button of the mouse here, I can extract the statistics from here, you see? These are the statistics of the original data. If I'm going to the data set that is calibrated and thus subtracted, I'm going to the vegetation, right-clicking on that, and I'm asking for the statistics. Now I have the statistics of this particular data. So you see here we have the two spectral signature. This is in the right part, you see we have the effects of the scattering. Here you see where I modeled the bottom of the atmosphere calibration. You see that I have really the spectral signature that is really similar to the theoretical one, because you see here I have the relative maximum reflection peak in the green, I have the absorption peak in the red, and the maximum reflection peak in the near infrared. You see, I'm closing that. So let's select, for example, now the water. Right-clicking with here, I'm going to the statistics, right part of the mouse. I'm taking this water and I'm dragging under the calibrating and thus subtracted data sets. Right-clicking here in the water, statistics from here, and you see that here the spectral signature is completely different. You see from here. So you see it's completely different as before, because you see we have a maximum of reflection in the blue band, in the second band of the blue. I have an absorption peak Yes, because it's reflecting the color of the sky, the small water southern part of Torino, that it is the reason. You see that I have an absorption peak both in the green and in the red bands. I have a peak of reflectivity in the near infrared, and then you see that in the mid infrared I have the reflection. I mean, there's a complete absorption. So you see that it's really different. So let's do another thing. Let's close that. Let's have a look again to the vegetation one. So this is the original data, the spectral signature of the original data, and now we are extracting the right-click in the statistics, the spectral signature of the calibrated and thus subtracted data. So bottom of the atmosphere, the scale of the x-axis of course are different because here we have a 0 from 1 that are reflectance. Here in the right part we have digital number, and you see that these spectral signatures are different, and this is the main reason that is compared you to those who is dealing with remote sensing in a very practical view. Because I mean, from now on, and you have fully understood from now that the calibration, the bottom of the atmosphere calibration is absolutely necessary. Because you see, taking into account the spectral signature, you see that it's fundamental to calibrate this data because the data are different after the calibration. So the calibration is something that is very important. That's usually who is dealing with remote sensing in a very practical way without having the theoretical basis is not calibrating the image. And you see, you can understand from this comparison with these two spectral signature that is, we should calibrate the data, and we should have this data calibrated in the bottom of the atmosphere mode. So this is simply that make you understood that these pre-processing radiometric calibration are absolutely necessary and must therefore perform every time you are processing data, if the data you are using are not already calibrated. So in this tutorial, in the first phase, we have see how to calibrate the data. In the second phase, we take into account how we can extract a region of interest and how to use this region of interest toolbox in order to extract some spectral signature and to evaluate the characteristics, the statistical characteristics of the data. And you can understand that, of course, the region of interest are very important because allows us to extract spectral signature. So let's close it. For today is enough. Let's exit this lab number 5, and we will meet for the lab number 6. And of course, as usual, thank you for your attention and never give up.